Oxidation-reduction reactions. These reactions are an important class of reactions formally involving the loss and gain of electrons. Oxidation is said to be the loss of electrons. For example, if zinc metal goes to zinc 2+, then it must lose 2 electrons. And reduction is classified as the gain of electrons. That is, if you have copper 2+ and add 2 electrons to it, it becomes copper, and the copper is reduced. Oxidation and reduction always occur together. There has to be somewhere for the electrons to go, so you can't have an oxidation reaction without also having a reduction reaction. So for example, zinc and copper react together, and the reaction involves the transfer of electrons. And in this case it's fairly easy to see, but it's not always the case. So for example, if you react hydrogen and oxygen to give water, we classify this as a redox or oxidation-reduction reaction. But the reaction of a proton and hydroxide to give water is an acid-base reaction. How do you tell the difference? Does it matter? Well, it turns out that it does. If you can classify reactions, for example, as a redox reaction or acid-base, it allows you to identify reaction types and predict what's going to happen. It'll save you memorizing all the reactions that you ever learn. Some students do try to do this, but it's not a very successful strategy. So to help you classify, one of the things that you need to be able to do is to identify redox reactions. And to do that, you need to look for changes in oxidation number in a particular element as you go from reactant to product. And as we'll see, oxidation numbers give some information about the distribution of electron in compounds. How to assign oxidation numbers. There is a number of rules, and the first one is that atoms in elements always have an oxidation number of 0. So in H2, the element hydrogen exists as H2 molecules, the oxidation number of H is 0. For a compound, the sum of all the oxidation numbers must equal 0, and for an ion, it equals the charge on the ion. So in sodium chloride, the oxidation number of the sodium is +1, because the charge on the ion, the sodium ion, is also +1. And similarly, for the chloride ion, the oxidation number is -1. Another rule. Oxygen is almost always -2, unless it's bonded to itself, which is unusual. If it is bonded to itself, the name will have peroxide in it. And H is usually +1. Oxygen is almost always -2, except when it's bonded to itself. And hydrogen is usually +1. So in H2O, water, the oxidation number of the H is +1, and the oxidation number of the oxygen is -2. And the sum of these, -2 for the oxygen and 2 +1s for the 2 hydrogens, is 0. Now this may seem a rather odd set of rules, but there is some rationale behind them. If you recall learning about electronegativity, you'll remember that it's the ability of an element to attract electrons in a bond. And electronegativity increases from left to right across the periodic table. So fluorine, oxygen, and nitrogen are the most electronegative elements. So if you take a compound like H2O, water, you remember that there's a small negative charge on the oxygen and small positive charges on the hydrogens. And what we do when we assign oxidation numbers is we just imagine that we're going to withdraw all the electrons in a bond to the most electronegative atom. So if we did this, oxygen would get 2 extra electrons and become 2-, and the H's would lose their share of the electrons in the bonds and become plus. And this is really the underlying idea behind oxidation numbers. They're just a way of electron bookkeeping, and it allows you to see whether the element has lost or gained a share of electrons during the reaction. Okay, so if we look at those reactions again, for example, zinc and copper, we see that zinc, during the process of being oxidized, goes from zinc 0 in the elemental form to zinc 2 plus. And copper goes from copper 2 plus to copper 0. So zinc is being oxidized, it's losing its electrons, and copper is being reduced by adding electrons and reducing the oxidation number. Now if we look at more difficult to assign molecular reactions, here's the reaction of hydrogen and oxygen. Right? And we decided it was a redox reaction. But if we look now at what happens to hydrogen during the course of the reaction, it goes from H2 in the oxidation state of 0 to H2O, where the hydrogen has an oxidation state of +1. That is, the oxidation state has increased. The hydrogen has lost its share of electrons, and therefore we say the hydrogen has been oxidized. Conversely, the oxygen started out as 0 in its elemental form and is now in the -2 oxidation state. That is, it's gained share of electrons during the reaction, and so we say the oxygen has been reduced. If we look at an acid-base reaction, however, the hydrogen, in the form of a proton, starts out in the +1 oxidation state and stays in that oxidation state as it turns up in H2O. And the same thing happens for the oxygen in hydroxide. It starts in the -2 oxidation state and ends up in the -2 oxidation state. So overall, there's been no change of oxidation number here, and therefore acid-base reactions are a separate category of reactions from redox reactions.